This website makes learning so easy. I found all my resources here.
Like what you shares.
All right, let's dive right into this explainer. Today, we're unpacking the invisible architecture of the universe. We're going to climb from the tiniest, most abstract mathematical particles all the way up to the cosmic scale. If you've ever wondered how these strict mathematical rules of quantum mechanics actually build the solid reality we experience every single day, well, you are in the exact right place.
So here's our roadmap for today. We'll be climbing this conceptual ladder, starting with states in Hilbert space, then moving through measurement and uncertainty, dynamics, composite systems, and finally, we'll wrap up with quantum statistical mechanics. Let's get to it.
Section 1. States and Hilbert space, the foundation of the quantum world. We really have to start at the very bottom here. What exactly is a quantum state? And, well, where does it live mathematically?
Now, the crucial thing to grasp is that this wave function isn't just some physical wave on a graph. It's not like a ripple in a pond. Mathematically speaking, it's actually a vector in a complex separable Hilbert space. Sometimes physicists just call this a ket. But the big takeaway here? This single mathematical object holds absolutely all the information about our particle. It is literally the ultimate blueprint of a quantum state.
Okay, before we go any deeper, let's lock in some of this jargon. You see, when physicists run experiments, they aren't just looking at one isolated particle floating in a void. A system is just a sufficiently isolated part of the universe that we're studying. And to figure out probabilities, they rely on a statistical ensemble, basically a massive number of identical copies of that exact system. And the formalism, well, that's just another word for the wave function we just talked about.
Moving on to Section 2, Measurement and Uncertainty, subtitled The Observer's Dilemma. Let's see how things get, well, incredibly weird the very second we try to actually look at or measure these systems.
Think about the contrast between our everyday world and the quantum realm. In classical mechanics, multiplication is commutative, right? Order doesn't matter. If you measure position, let's call it x, and momentum, p, then x times p is exactly the same as p times x. But mathematically, the quantum canonical commutation relation completely flips this. Multiplying position and momentum operators in a different order leaves a non-zero remainder, specifically I times Planck's constant, h bar. So yeah, in the quantum world, the order you do things fundamentally changes the outcome.
And that brings us directly to how we actually measure things. When we measure a quantum state, it doesn't just passively reveal its properties. The measurement is an active, honestly, kind of violent event. Born's rule tells us the probability of finding the particle in a specific state. But the moment we measure it, the wave function undergoes what we call a collapse. It's an instantaneous transition from this fuzzy, probabilistic state into a definite reality. And that expectation value, that's simply the average outcome we'd get if we measure that massive statistical ensemble of identical systems we mentioned earlier.
Why this matters is absolutely staggering. You might be familiar with the Heisenberg uncertainty principle, but the Robertson-Schrödinger uncertainty relation is like its big, intimidating upgrade. This mathematical relationship proves that the universe literally forbids us from knowing incompatible properties like position and momentum with perfect accuracy at the exact same time. The tighter you squeeze one measurement, the more the other one violently slips out of focus. It's a hard, undeniable limit on reality itself. All right, Section 3, Dynamics and Approximations. Moving particles and solving the impossible. So we know what a state is, but how do these particles actually move over time? And, maybe more importantly, how do physicists do the math when things get way too complex to solve perfectly?
Let's start with a particle that isn't really moving in the traditional sense. If you ever hear a physicist mention a stationary state, what they actually mean is a state of definite energy. It's an eigenstate of the Hamiltonian operator. Think of it kind of like a perfectly vibrating standing wave on a guitar string. The wave itself is vibrating, sure, but the probability of finding the particle at any given location, its static probability density, doesn't change at all over time.
But what happens when we zoom out to an entire molecule? Well, the pure Schrödinger equations suddenly become literally impossible to solve perfectly. So physicists cheat, and they do it brilliantly, using the Born-Oppenheimer approximation. Because atomic nuclei are massively heavier and slower than the electrons zipping around them, physicists mathematically clamp or freeze those nuclei in place. They totally neglect the nuclear kinetic energy for a second, just so they can study the fast-moving electrons. This clever trick creates a potential energy surface, and honestly, it's what makes calculating molecular chemistry actually possible.
Another amazing mathematical tool is the WKB approximation, which beautifully bridges the quantum and classical worlds. When a physical potential changes very, very slowly over the scale of a particle's wavelength, we can actually treat these quantum particles almost like classical objects. Well, that is until they hit a barrier. When the particle hits a classically forbidden turning point, the math has to smoothly connect the oscillating wave to a decaying exponential wave, and the particle suffers a quantum phase shift. It's this perfect, elegant blend of classical intuition and complete quantum weirdness.
Which brings us to Section 4, Composite Systems and Entanglement, Identical Particles and Spooky Connections. Let's step up the ladder again. What happens when multiple quantum particles are forced to interact with each other?
Okay, so a fundamental truth of our universe is that everything, literally everything, is divided into two strict camps based on their spin. In camp number 1, we have bosons. They have integer spin, symmetric wave functions, and they're the force carriers, like photons. Bosons absolutely love to group together in the exact same state. They're super social. Then in camp number 2, we have fermions. They have half-integer spin, antisymmetric wave functions, and this group includes things like quarks and leptons. Fermions are the building blocks of matter, and as we'll see in a second, they are strictly antisocial.
Because those antisocial fermions have antisymmetric wave functions, they are tightly bound by the Pauli exclusion principle. Mathematically, if you try to cram two identical fermions into the exact same state, a matrix calculation known as the Slater determinant instantly vanishes to zero. The universe just deletes the possibility. No way, not happening. And this right here is exactly why matter takes up physical space. The electrons in the atoms of your shoes absolutely refuse to share a quantum state with the electrons on the floor. It is literally the only reason you don't instantly fall right through the ground.
Now let's see how this builds into something even stranger. 2.828. That highly specific number is known as Chirleson's bound. It is the maximum quantum violation of the classical Bell-CHSH inequality. See, in a purely classical universe with hidden variables, this correlation value could never ever go above 2. But quantum entanglement shatters those classical limits, reaching all the way to 2.828. It mathematically proves that entangled particles truly affect each other's measurement outcomes instantaneously across space. It totally defies our everyday common sense feeling of locality. And because of how delicate and intricately connected these quantum states are, we run into something called the no-cloning theorem. It dictates a very strict rule. You cannot simply copy and paste an unknown quantum state. If you have a blank quantum state and try to use a unitary operation to perfectly duplicate an unknown state onto it, the math proves it's impossible to do without completely destroying the original. So, yeah, you can never have a perfect backup copy in the quantum realm. It's a one-of-a-kind deal.
And finally, Section 5, Quantum Statistical Mechanics, the macroscopic magic of quantum gases. For our final step up the ladder, let's zoom all the way out to see what happens when you get billions of these indistinguishable particles together at absolutely freezing temperatures. Remember our friendly, highly social bosons from earlier? Well, if you get a massive gas of bosons and cool them down below a very specific, critical temperature, something purely magical happens. They undergo a phase transition called a Bose-Einstein condensation. Because they are perfectly allowed to share the same state, a massive macroscopic fraction of the entire gas condenses into the exact same zero-energy ground state. The whole gas basically syncs up and starts behaving as one single massive quantum superstate.
This phenomenon brilliantly illustrates the grand divide at absolute zero. When you compare a Bose-Einstein gas to a Fermi direct gas, the difference is absolutely stark. At absolute zero, bosons all crash into a single ground state, exerting zero degeneracy pressure. But the fermions, because of that Pauli exclusion principle, they still refuse to share a state. So even when frozen solid at absolute zero, they have to stack on top of each other, filling higher and higher energy states up to a limit we call the Fermi energy. This forced stacking creates an intense outward mechanical pressure.
And the real-world consequence of that mathematical fermion stacking is just mind-blowing. That outward stacking pressure, called degeneracy pressure, is so unimaginably strong that it operates on a literal cosmic scale. When a massive star dies and gravity tries to crush it down into a black hole, it is literally this exact quantum pressure, fermions stubbornly refusing to share a state, that holds up dead, collapsed stars like white dwarfs and neutron stars against the crushing vacuum of space. How wild is that?
Which leaves us with this incredible, mind-bending thought to close out our explainer today. We've seen that particles are abstract mathematical vectors that collapse the moment they're observed. We've seen that entanglement links them instantly across the entire universe, and that the only reason matter is solid is because of an anti-social mathematical quirk of fermions. If the foundational building blocks of reality are this deeply strange, probabilistic, and interconnected, well, what does that say about the solid, predictable world we think we see every day? Keep pondering that one, and we'll see you in the next explainer.
Like what you shared.
This website makes learning so easy. I found all my resources here.